Hi everyone. Welcome to this binary search problem solving series. Today we are going to discuss another interesting problem on binary search. The problem statement is like we are given an unsorted array of n distinct elements and we need to find the local minima. So the definition of local minima is that it is an element which is smaller than its adjacent elements. Okay. So for example, let's say that we are given this array of unsorted elements. So we need to find the local minima here. And like we can find only one local minima. We don't need to find all the local minimas here. So any one local minima is fine. So for example, here if you would observe that we need to find an element which is actually smaller than its adjacent element. So let's just say that for 7, if it is smaller than what are the adjacent elements to 7? So on the left hand side there is no element, but on the right hand side we can say that 5 is a adjacent element to 7. But 5 is not smaller than 7, so we cannot say that 7 is our local minimum. So if we move it, let's see 5. So for 5, 7 and 8 are its adjacent elements. Okay. So, and we can observe here that 5 is smaller than its adjacent element, both 7 and 8. 5 is smaller than both 7 and 8. So we can say that 5 is our local minimum, right? So 5 is one of our local minimums. Let's just move it. Now for 8, what are the adjacent elements here? Those are 5 and 6. But since 8 is greater than both of them, so it is not a local minimum. Then for 6, we can say that 8 and 2 are its adjacent element, but 6 is greater than 2, so it is not a local minimum. For 2, we can say that it is smaller than 6, but it is greater than 1, its adjacent element, so 2 is again not the local minimum. Now for 1, we can say that it is smaller than its adjacent element. It is smaller than 9, it is smaller than 2. So 1 is one of our local minimas here. Okay, so 1 can be a local minimum. Now for 9, we can say that its adjacent element to the right, there are no elements. So on the left, it is only having 1. And 9 is greater than 1. So again, 9 is not our local minimum. So as you can see from the array that there can be multiple local minimas. We just need to return one local minima in the array. Okay. So while doing this, Brian, you must have got some hint, right? Like we can go ahead with the linear approach, and for every element, we can check whether it is smaller than its adjacent element or not, and we can ultimately return an answer. Right? So, like, let's just say that our approach one is linear search. Check for every element where if smaller than its adjacent element, we can return it. Okay. So we can like this will be very straightforward. I'm not going to code this solution. Like it is just a linear search and we are going to check for every element. It's index -1 and index +1, whether it is smaller than both of them. And if it is, we can just simply return that answer. So the time complexity, we can say in the worst case scenario, we are finding our local minima at the end. So we can say that we end up traversing complete L. The time complexity will be O of n and the space complexity will be O of 1 because we are not taking any extra space, right? We are just traversing the array and checking the elements, right? But again, let's just say that it can work. This linear search approach can work for certain set of constraints. Okay, like if our array length is within 10 raised to the power 9 or less than 10 raised to the power 9, then this linear approach can work. But what if our array length, let's just say that our constraints are like the n can be greater than 10 raised to the power 9. Okay, 10 n can be greater than 10 raised to the power 9. Our array size can be much larger. So in that situation, linear search won't work here. We need to come up with some optimized approach to actually solve this problem. So now if we observe here that it is the only game of searching here, like we need to actually find that element within this array which is smaller than this adjacent element. So one optimization over linear search is the binary search. Okay, so let's just see that how binary search can be applied here. So approach to, like, ultimately it's the binary search. Binary search. So how binary search can help us here? So the main fundamental of binary search is that we need to define a certain search space, right? So search space is basically the area or the, like you can say the quantity or the area in which, or the data structure over which we are actually going to search our solution. Like for example, we are provided this array here, so our search space can be this complete array, or it can be a certain range of numbers. If you have seen other problems in this series, right, where we have applied binary search, we have defined our search space where we are searching within the minimum and the maximum element in the array, a certain range of elements. Or we sometimes search over the complete array, which has been provided to us. So the search space can be anything here. Okay, so first we need to define the search space, like what will be the search space over which we are going to apply our binary search. And the second thing we need to define is the target, like what actually we need to find. Okay, so let's just go one by one here. So for the search space here, as we can observe here that our local minima is ultimately going to be lying in the array itself, right? It cannot be any other element which is not the part of this array. Okay, it is going to be any one of the elements within this array. So we can clearly state that our search space is going to be the complete array provided to us, right? Whatever arrays has been provided to us, we are going to apply binary search over this complete array. And what is our target ultimately, like what we actually need to find here is very straightforward, that we need to find the local minimum, or you can say the element which is actually smaller than its adjacent elements. Okay, or element which is smaller than its adjacent elements. So while applying binary search, we are going to do the same thing like the linear search, checking for that element, whether it is smaller than its adjacent element, and then we move forward. But one optimization which binary search does and which linear search doesn't is that binary search considers only half of the array and it discards the other half of the array. So that discarding of the other half of the array is actually defined by the conditions which we apply over the binary search, right? So basically, binary search will be searched, like we will be discussing those conditions. What the conditions will be, okay, in which we can actually search the half of the array, and then we will be keep on discarding the other half of the array. Okay, so let's just discuss those conditions here. Okay. So one thing is that ultimately to discuss the conditions, I would need to draw a sort of graphical representation as to how we are actually going to do this. So since I'm not having any of those graphic pens also, so I will be doing my best to actually utilize Paint to actually demonstrate how we are going to come up with the conditions here. So let's just consider this example itself. Okay, let me just copy this once and let me just paste it. So this is the array which has been provided to us, right? Okay, right. Okay, so this is the array here, 7586211. Okay. So let us just visualize this, like how the elements are actually structured. Let's just say that after 7 we are getting this dip of 5, right? So we move down. Okay. Now after 5 we are getting 8, so which is again incrementing. Okay. Now after 8 there is again a small dip which is greater than 5, so there is a huge dip. Now after 6 we are again getting small increment, that is of 2. After 2 there is a small decrement here which is of 1, and after 1 there is a huge increment here which is of 9. So this is actually our how our array is going to be represented in a graphical format, if you could observe. So let me just label this once as well, so it becomes quite easy to track. So here is 7, Here is 5, here is 8, which is increasing. Then it is again decreasing at 6. Then it is again in, okay, sorry. I think I did a mistake. Like for 2, I incremented. My bad. Let me just, so sorry. So after 6, actually, we are getting 2 here, right? So it is again going to decrement. Then for after 2, we are again decrementing to 1. And then after 1, it is incrementing. So this is how it is going to be represented. So after 6, we can say here it is 2, then it is 1, and then it is 9. Okay. So this is how the array is. Like after 7 we get a dip, then we got an increment, then it is actually descending order here 8, 6, 2, and 1, and then it is suddenly increment. So in the solution we saw that what are our local minimas. It was 5 and 1. So as you can observe here that 5 is the one local minima, and then there was 1 which was the local minima. So what you can observe from this thing is that at an element which is at present at the dip position, right? Those elements are actually forming our local minimum, right? Whenever there is a dip, sudden dip and then an increment, at that position we can say that we are having our local minimum. If there is consistent dip, like as you can see here, if there is a consistent dip, we are not having 6 is our not our local minima since it is consistently decreasing. But 1 is our local minima because there was a dip here and then it is increasing after that. Right. So this is actually going to form our conditions here, right? From this, we can certainly deduce some observations. Okay, let's just change the condition. Let's just say that, for example, instead of 7 here, okay, I'm having 1. Let's just say this. So if there had been 1 here, okay, let me just draw this. So 1 would be here. Okay. So now how the local minimum would have changed, right? How the local minima is changing here. If you could see here that this 5 here, this is 5 here, and this is 1, and this is 5, then this is 8, and this is how it is structured. So now can 1 be a local minima? Can 1 be a local minima? If we like read the question, it states that it should be smaller than its adjacent elements, right? And ultimately 1 is not having any adjacent elements to its left, but eventually when we are moving forward here, it is having a greater elements on its right. So 1 is actually smaller than its adjacent element. So we can say that our local minima is now 1 and not 5 here, right? So our local minima is 1 and not 5 here. Okay. So one thing here is that we can actually say that at the edge positions like here and here, we can clearly state that if our edge position for 0 index, we can say that we are not having any element to the left. So if the element to its right is actually greater than it, or you can say that if this 0 index element is actually smaller than its element adjacent element, that is at present an index 1, which is actually smaller than it, then we can simply return that this will be a local minimum, because ultimately according to the question we have to return only one local minimum, right? So one condition here is like which we can deduce from the observation is that check for 0 index, 0th index, if it is smaller, and again we can check for 0 index and we can check for the last, that is n minus 1th index. Had it been here, let's just say that had it been 8, for example. So if after 9 there had been an 8 here, so there would be a, then we would have a dip here. Okay, and we can just name it as 8, right? So can we say that adjacent element to 8 is actually 9 and there is no adjacent element on its right? So again, 8 can also be a local minimum, right? Because we are only having one adjacent element to 8, which is 9, and it is actually smaller than 9. So again, this can be a local minima here. So we can say that our condition, like check for 0th index and n minus 1th index, like if it is smaller than its adjacent elements, then we can clearly return our answer, right? We can clearly state that those index those index element can be our answer. And if it is not, right, if it is not, let's just say that we again revert this to our original array itself. Currently what area has been provided to us. If it is not, like currently according to this example it is not, so we can continue searching within this array. Now we need to, within this graph, we need to actually search for those elements. If we had an array such like this, 7 5 8 6 2 1, so let me just revert these conditions back to those things, because I needed to explain this base conditions here so that we can actually come up to the solution. Okay, so let me just do this once. So it was 7 here, right? It was 7 and it was 9 here. Right, it was 9. 7 5 8 6 2 1 9. So now, as we found like earlier, we have checked for the base conditions. Now we need to say that since our base conditions are not matching the criteria, now we need to search within this array. Inside the array, we need to look for our local minimum. Okay. So now there can be certain conditions or situations which we can encounter. First thing is that let's just say that we come at this particular position. Okay, let's just say that we come at 8, this index 8. So by applying binary search, if we are coming at this position index, like let's just say we are coming at this 8 element, what can we observe from here? We can say that both of its left side element and both of it and the right side, we are having a dip on both of its ends, right? So our local minima can be lying on any either of the sides, right? Because 8 cannot be a local minima because it is greater than both of its adjacent elements, right? And since there is a dip on the left hand side as well as on the right hand side, so we can say that our local minima can be lying on either side of this. Right, it can be either on the right hand side or it can be either on the left hand side. So if we are going on the right hand side, right, if we move forward to the right hand side, we come at 6. Now for 6, like for 6, can we say that on the left hand side it is actually incrementing and on the right hand side it is actually decrementing? So ultimately, if I go back to above, like if I go again back to left hand side, can I actually find my local minima in such a way? I'm just saying that if like we actually end up after binary search, if we end up at this particular index, right, and if our adjacent elements are smaller, both of the adjacent elements smaller, so we can say that we can move in either of the directions to actually find a local minimum. Now, when we decide to go right, and ultimately we land up at a particular index, let's say this particular situation where we encountered an element which is having the left element or the element lying to its left which is greater and the element lying to its right which is smaller than it. So should we be going to the left or should we be going to the right? That's the question here. In which direction should we go, or you can say which search space should we discard? Should we discard this particular portion or should we discard this portion? So the answer is, like you can say that going above, we cannot actually find our local minimum, because you can clearly see that if we are going above, right? If we go left to the 6, we are actually incrementing. Its adjacent element is actually 8. So we can say that it is going to increment. We don't know if it is actually going to increment, but we can say that it is actually it will increment somehow. But on the right hand side, we can be sure that since it is decrementing, we can be finding our local minimum. There is certain sort of surety here. So for a situation where the element, if it's any of the adjacent element is smaller and any of the other adjacent element is greater, we will move towards the smaller side. So for any element, if one of its adjacent elements is smaller and one is greater, we will move to smaller side, because it actually gives us hope that we can actually find our local minima here, right? We can actually find our local minima here. And this similar situation is also for the case where, like, let's just say that this is a situation. Okay. So here is, let's say, 3. Here is, let's just say it is 6. And here is actually 9. So here, if you would see that for 6, its adjacent element 9 is greater, but the its one of its adjacent element is smaller. So we will move towards the smaller side, right? So this covers one case here. So till now we have covered two cases. One is that we check for the last index and the first index whether it is smaller than its adjacent element. Then we are actually checking this particular condition where it is consistently decreasing on one side, right? It can be consistently decreasing on the left hand side, or it can be consistently decreasing on the right hand side. So in this situation, we will move towards the decreasing side. This is another situation, right? If and now then, if is there any other case which we need to discuss? Right. So then there is this one which we didn't know. So for this situation where it is actually kind of a maximum, you can say, like a situation where both of its adjacent elements are smaller. So we can say that in that situation we can move to either side. So if for any element it is greater than both its adjacent elements, we can move to either side, because we cannot deduce from this position like whether I'm going to find my local minimum on the left or on the right, because both side it is decreasing. So we can move either side to actually find that local minimum, right? And by this we are actually covering all of our you can say the base conditions for the binary search here, right? So let me just uh, like do a one dry run first, so in order to actually understand how this thing will be working, or how these conditions will be actually coming into picture, and how we are actually going to apply our binary search. Okay, so as per our search space, we are actually traversing over the complete array. So our left index, you can say, let's just say that our left index is going to be 0, and our right index is going to be n minus 1. Here, how many elements are there? 1, 2, 3, 4, 5, 6, 7. So our right index is going to be 6. And let me just draw the table so that it becomes further clear. Uh, 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 right. So this is our left, this is our right. Then we are going to get a mid, and then we are going to check with the conditions which we have defined where we need to go. Right. Left. So now, initially our left is 0, our right is 6. So our mid element here will be what? 0 plus 6 by 2, that is going to be 3. So 0, 1, 2, 3. We come at 6. Now for 6, if we can see, for 6 we are having this situation. We are going to check whether it is um, in which condition it actually falls. Right, so it is actually falling for this condition. Second, for any element, one of its adjacent element is smaller and one is greater, which we can observe here from this. So we are actually going to move from towards the smaller side. So this for 6, or you can say for index 3, the smaller side lies on the right hand side. So we can say that we need smaller side, or you can say the small lies on right. So we can say that we need to go right, and we can discard our left half. So how are we going to discard that left half? Is by incrementing our left index by mid plus 1. Okay. So what we are going to do here is we are going to increment our left by mid plus 1. So that is going to be 4. Now our right is like 6. So mid is going to be 5. 0, 1, 2, 3, 4, 5. Now we came at 1. So now for 1 we again run those conditions which we are actually checking, that whether it is like this condition will be checked very initially at the first before even applying the binary search. The number one condition we are going to check before even applying the binary search. So we are left with these two conditions. So if for the element if it is smaller than, if any one of the element is greater, like if it is continuously decreasing or increasing, okay, so it is not. Then if it is greater, if the adjacent elements are greater on both the sides of it, it is not. So we can state that for this element, neither of the conditions in which we actually need to discard an array is met. So we can say that this particular, element is our local minimum. Well, minimum. So we actually found our local minimum, right? This is just a small example as to how it is working, and this graphical representation is actually helping us to getting those conditions. So let us just code this out, like how we are going to now apply binary search here. So let's just say that we are defining this array here. So let me just copy this array once, something like this. Okay. Now our left is going to be 0, our right is going to be length of a, which is so len a minus 1. Right. First, we actually need to check for this condition even before going towards the binary search. First, we will check that whether our 0th index element is smaller than this adjacent element, or the n minus 1th index element is smaller. So before even applying and going ahead for binary search, we will check if a of 0 is smaller than a of 1. So we can clearly print that our answer as a of 0. Okay. Or else we are going to check elif. We are going to check if a of n minus 1, or you can say in Python we can use minus 1, is if it is smaller than a of minus 2. So we can actually print, if it is smaller, then we can actually say that a of minus 1 is our local minimum. Correct. Else we are going to apply binary search here. You can actually take care of the base conditions, that if the length of the array is only 1 and other things like that. So now we are going to apply binary search, because if those two conditions are not met, then we need to actually search for a local minima within this array. So while left is less than equal to right, right. So we are going to actually find our mid index first. So that is going to be left plus minus left by 2. That is our mid index. Now for this index, we are going to check for these two conditions, right? If it is continuously decreasing, or if it is continuously, or if it is the maximum, that is both the adjacent elements are greater. Okay. So how are we going to do this? Let's just see. So we are going to say that if a of mid minus 1, right? If A of mid minus 1 is greater than A of mid and A of mid is smaller than A of mid minus 1. Oh, sorry, mid plus 1, not mid minus 1, because here we are actually checking that if mid minus 1 is greater and mid plus 1 is also greater. Right. Basically, we are checking for the minima condition here. If here we are checking if adjacent elements are actually greater or the current element is smaller than the adjacent element. Right. Checking for local minimum. If current element is local minimum. So in this situation, we can simply say that our answer is going to be A of mid and we can break from here. If that is not the situation, if the current element is not our local minima, so then we need to see or we need to evaluate these conditions here, whether it is consistently decreasing on either side or whether it is a maxima element, or you can say it is bigger than either of its sides. Okay, so we are going to do is A of mid. If it is greater than A of mid minus 1, okay. If A of mid, if my middle element is greater than my mid minus 1, let's just say for 8, if it is greater than my mid minus 1, then I can say that I need to go towards the right, or let me just write the complete condition, so which should be at par with our provided condition. So we are now going to check if A of mid is actually greater than A of mid minus 1 and A of mid is greater than A of mid plus 1. So this is the condition of maxima, we can say, or you can say local maxima. Element greater than both adjacent elements. So in this situation, we decided that we can move either side, right? We can move to either side. So let's just say that we move to left hand side. So right will be mid minus 1. We decided to move to left hand side, right will be mid minus 1. Else, if this is not the case, so it is actually decrementing on either side, right? If the element is not in this situation, which is a, it is not greater than both the elements, so it should be lesser than any of one of the elements, and we are going to move in that direction. So else, we can say that if A of mid is actually smaller than A of mid minus 1, that is, if it is, you can say, right, so if A of mid minus 1 is actually smaller than A of mid, right? So A of mid minus 1, that is this element, if it is smaller than A of mid, then we move towards the left hand side. Like if this is our A of mid, so and if mid minus 1 is smaller than this, so we are going to move in that direction. Mid minus 1, so that is right is going to be mid minus 1. We are going to move left. Or else we can say that if that is not the situation, then we are going to move left, right. That is left is going to be mid plus 1. So this is decreasing on left, and this is the situation where it is actually decreasing on right, right? So this is how our if else conditions are going to be, and this is how we are actually going to return our answer. So let's just say that the answer is 0 currently, and now for this A, just run this code and see what the answer is. So it returned 1. It returned 1. That means that it actually found this particular element to be a local minimum. Now let's just change this to some different thing. Let's just say that, okay, if even if you are having negative elements, it won't pose any issue. It is 6, 6, 9, 3. 7. Right. Again, if you would see that one, its very first conditions are not being met. One is not smaller than -1. 7 is not smaller than the adjacent element. So we are actually going to search within this cell. Let's see that what actually binary search returns. It returned 3. So here you can clearly see that 3 is actually our local minima. It is smaller than 9. It is smaller than 7. Right. And if I actually made it 10, now let's see what it actually returns. Okay, so it actually, we now get two answers, right? Because ultimately we actually, this condition became true. 7 is smaller than the adjacent element, that is 10. So it actually, we printed 7. And then there was no other local minima within this eventually. So the answer is actually coming out to be 0. Or you can say it is actually coming out to be -1. So is it true that there is no other local minima? Like for -1, we can say that -1 is actually smaller than 1 and it is also smaller than 6. So it didn't actually return for that. Interesting. It should have returned, or I think that, yeah, it now returned -1. But yeah, like it is actually -1 here. So I think that this problem doesn't work from -1, or there must be some logical mistake here, which I must have committed within this if else condition it is not working. But so and so, this is how binary search is actually, optimizing our searching of the local minima within this unsorted array, right? So by this, it actually meets our constraint, even the array size becomes greater than this. So we can clearly state that binary search will take the time complexity of only log n, log of n, since we are actually discarding certain half and only consider other half of the array, right? And the space complexity again is going to be constant here. So I hope you learned something from this. Do try this question out yourself and look into various different conditions and let me know in the comments, like, if any other mistake or conditioning has been, done wrong, so that I can also learn from those things, right? So thank you for watching. Have a nice day.